This is the Amp Hour Podcast, recorded March 3rd, 2015. Episode 239, with guest Colin O'Flynn, Aspirated, Adamantine, Attacks.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Colin O'Flynn.
Welcome, Colin.
Is that a Canadian accent I hear?
Yeah.
You got that from that? Last name O'Flynn, and you say, are you Canadian?
Yeah, the middle name's Patrick, too, so it's excessively...
Right.
Favorite day of the year, March 17th?
Yeah.
Well, welcome. And Colin is part of the, well, no, not part of, he is, welcome, the Chip Whisperer.
Thank you.
Shh, whisper, 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 whisper.
As long as Cesar Millan doesn't sue me, it's fine. Yeah. Sort of the...
Right.
or Robert Redford,
and
right?
Very timely, yes. Very timely, because I just released a mailbag video yesterday with your Chip Whisperer project in it, which, as everyone should know, because everyone follows, anyone who listens to the show, I'm sure, followed the Hackaday contest and knew that you came second in that. And they may not know that you've got a new Kickstarter for a Chip Whisperer Lite.
They do now.
So they can go buy one. Well, they do now.
Yeah, make sure you put in Dave's name as the sold by, and then he gets 10%.
Oh, do I? Hey. All right. Now we're talking.
Kickstarter's upgrading.
Yeah.
Yeah. I think that should be a feature in Kickstarter. A
like an affiliate program?
System. An affiliate program. They could... A commission-based thing.
Yeah, they already have that, Dave. It's called The Money Goes to Kickstarter.
Right, the money, right. They're the ones who get it right, yeah. Got it.
So, Colin, let's talk about security, because I think this is an interesting topic. I don't know if we've talked about it much on the show before. Maybe when Mike Ostman's been on, but
we've touched on it, but we've never talked about the level of detail you're capable of doing with this project, though.
So, security. Why security? Why embedded security? What's the deal?
All right, so the basic deal here is that we get a lot of people doing stuff, they want to protect maybe their IP of the product, and they say, I'm going to throw AES 256 on my bootloader, and it's unbreakable because according to the government, that you can use AES for like top secret protection of documents. And the problem is that when you implement it on real embedded hardware, there's these fundamental issues. Like it takes a certain amount of power to set more lines high than it does to set them low. And you can basically measure these tiny power differences and break the encryption algorithm that's running on these embedded systems. So it's, it's not just a checkbox. You can't say, oh yeah, I got AES, we're done, go home type thing. So
because it was designed, is it because they didn't think about the embedded platform when they designed that standard? They thought, it's running on computers which nobody has physical access to, therefore it's unbreakable.
Yeah,
is that?
I think at the time, I don't think they really knew about these attacks, but I mean,
right.
Even now, it fundamentally, they're almost unprotectable. So there's some things you can do in hardware, like you can have balanced registers, so it sets one line high at the same time it sets one line low, so you can't see any switch,
so it masks out those current pulses.
Yeah, exactly. So, but this costs more area. So if you're just doing, like a XMega or some sort of standard hardware peripheral,
chip. Yep.
You're not going to waste the silicon on doing that fancy stuff.
Because there's dedicated encryption chips, isn't there?
Yeah, exactly. So things like smart cards,
right, and they would probably have something like this, I'm assuming.
Yeah, exactly.
So they're designed because
they have good money behind it, right? So that's what really differentiates them. But a lot of people don't realize that. They'll use a regular chip and just say, "Oh, we're doing software. It's fine."
Right.
So,
but it stops the majority of people, though. But it's
like
not
a
going to
lock
stop
on your house, right? That kind of idea, of
right?
Stops people just from directly
stops the honest people.
Yeah, right, exactly.
Yeah.
But before the chip whisperer came along, how hard was it to? Is there a word for this for decrypting security based on power line checking?
Yeah, so the whole field is really officially would be called side channel analysis using power analysis. And it's more frequently referred to as DPA or differential power analysis, which is the first real algorithm published in this area. And so people have been doing it for a while. Like this was published in 1998. And there was commercial hardware. Like you could buy setups for doing the attacks. And I've never got an official quote, but it's on the order of $30,000 to $100,000 for these setups, right?
Yep, yep. For serious people.
So so before this, and a lot of academics do it. Like you can use a regular scope, but you've got to script everything in MATLAB and stuff, and no one really shares that because it's some PhD has spent a while making it, and he doesn't want to just publish it freely.
No, he wants to go make a startup so he can make a $50,000 machine to sell.
Yeah, exactly. Right.
That's right.
So finally pay off those student loans.
Yeah, that's it.
So wait, I want to take a step back then. How did you get into all this? Because again, the whole security field, like, I went to DEF CON, got to meet you. You were there, right? Mike was
I think
there.
we ran into each other once.
Yeah, well, we saw each other at Solid as well.
Yeah.
But I never really understand this. Like, did you come in from the IT side, or like it feels like that's a lot of people are coming in from the IT side, but not necessarily, and then kind of getting into the hardware real deep. So how did you get into all this?
Starting with your background, like your actual career.
Oh, okay. Way at the beginning.
Yeah.
Where do you come from? I was born in...
Yeah. Well, when I was a wee lad, I liked fans.
Start with your first job.
I was about 19. Sorry.
Yeah.
Am I allowed to make a boot jokes? Can I say a boot? Is that cool?
A boot? Yeah. Don't worry about it.
Sorry? What's this boot joke
No.
business? Sorry, that just flew straight over my head.
No. Canadians say a boot instead of about. It's endearing.
Oh, right. Okay, right.
Yeah.
Got it. Yeah. Now you get it.
Boot.
You can speak fluent Canadian now.
You'll just be able to trick everyone where you're from.
Yeah.
Right. Just like I can do fluent Yankee speak if I just speak in a southern accent, like a southern hick.
Which you think is a southern
small
accent, of
town
course,
accent.
right?
Yeah, right. That's right.
Anyway, sorry, Colin. Go ahead.
Anyway, sorry, go.
Yeah, so I started all sort of as a hobbyist, really, is most of my background. And I did electrical engineering in school. And during that time, I worked at a place doing gimbaled cameras. So the, cameras in the bottom of helicopters and stuff like that. So that was a lot of fun.
Right.
So I did that for a few summers, as an intern or whatever you call it type thing. And after that, I worked with Atmel in sort of the low power wireless division for 3 years. And a lot of that was Internet of Things and all that stuff. So obviously you get sick of Internet of Things once you spend more than a year in it, basically, is the...
We've got sick of it after talking about it for a year.
Yeah, right. That's as much as you can deal with. So, yeah, and then after that, I went back to school. And originally I was doing magnetic field communications and switched. I'd seen a presentation on this whole area of, side channel analysis and sort of said, oh, wow, that's super cool. And yeah, basically switched my whole topic. And that more or less brought me to
Is
here.
this your a master's thesis or something? Did you go back and do...
Yeah, so after doing the bachelor's, I went back. The plan was to do a PhD. So start with master's, then switch into the PhD. And
then sell a device for $50,000.
Yeah, somewhere along the line, right? So, yeah, all my background's embedded. That's really where I came from. And I'm in the security field. And it's always a bit scary because at DEF CON and stuff like that, like I just have a Windows computer and, I don't really care. It's not encrypted. Right. It's not any of this thing. I think when I was at DEF CON, I bought some stuff from DigiKey while I was there because I really needed something. So I was like, you should not be doing this. You're
on the grid.
Yeah. Well, you put in your credit card in this DEF CON network, but... Nothing happened.
Didn't end up on the wall of sheep, though, huh?
No, yeah. I had VPN. I was careful,
There
but
you go.
still,
Oh,
I don't
yeah,
know.
yeah.
I only
Oh,
vaguely
well, there
know
you
what I'm
go.
doing, right? So
So this is your master. This topic is your master's thesis, is it?
yeah, well, will be my PhD thesis. That's
Oh,
where
right. It will be your
stands,
PhD thesis. Okay.
And where are you studying?
Dalhousie University here in Halifax, Nova Scotia. So
Nova Scotia, which is so I grew up next to Canada and Buffalo, but I don't know much about Canadian geography. But I looked at pictures and it looks friggin' beautiful up there.
I was just going to say it sounds cold.
yeah,
That's all
they
I
only
can
show you
imagine.
photos of it in the summer, right? That's
I
the
did
trick,
notice
so.
that.
Ah, right.
Yeah.
Okay.
But yeah, in the summer it looks beautiful. It really
Yeah,
does.
it is. 2
Yeah,
months,
yeah.
right? Like,
yeah. That's cool though. Yeah. So
Right, so
Dalhousie.
this makes sense. Why it is so in depth. This actual project, it seems like more than what just some hobbyist would do as a side project. You've just put too much work into it.
This
and
is your
why-
$50,000 thing, but you forgot to charge
Right,
that
this
much.
is-
yeah, exactly.
Yeah, you
so.
forgot. You're doing it wrong. You're doing it wrong. You're paying big money to do a PhD and you're giving it away open source. What's wrong with you, man?
Yeah. Well, it's funny. I talk to ever so often. There's people interested. Oh, we want to invest in what you're doing, but it's like, no, I'm giving it away. By the way, so like, oh, how could you do that? It's
But
foolish.
you can still invest in open source hardware. Startups, MakerBot. Hey, they were open source and
true.
they got bought out for $400 million, $500 million or something.
625.
Really?
625. Sorry.
Just calling it like I see
So
it, man.
yeah, no, I would actually call them back and say, look at MakerBot. I'll be the next MakerBot.
Yeah, right.
So that can be your pitch presentation. I'll be the
Just that, no questions.
right. No, that's it.
Yeah.
So a PhD so what is the PhD? Is it like an actual crypto PhD program, or is it like just embedded, or what does that involve?
Yeah, so the PhD here at Dal, it's a pretty small school. So I don't know if there's like 20 profs in the electrical department. So my PhD is really electrical engineering. My supervisor does communications and radio and antenna design type work. So there's no real embedded crypto. I sort of was on my own here. And I got funding. There's a Canadian, research council that'll fund you more or less. So I have funding to do effectively
nice.
whatever. You get paid for 3 years.
That's great.
Should be done. So yeah, I mean that's part of the reason it's all open and free like that is there's no one
Right.
saying
Because
we
you're not
want-"
paying for it.
Yeah, exactly, right? So
And from what I hear, I mean, I have some friends who went through PhD programs. I didn't myself, but like, you're pretty much on your own no matter what you're doing. I mean, like, you can have an advisor maybe that's kind of guiding you along, but it's research. You're trying new things.
yeah.
So yeah, you're out in the wild basically.
yeah, it depends. I mean, some people their supervisor really tells them what to do, but I mean, I prefer to not. I'd rather just show up every week and see what's happening.
So did you have the idea for the Chip Whisperer from the start of your PhD, or did it just eventuate because this would be cool to? There's nothing out there. I'll actually produce something. Did you start out doing with hardware in mind, or just the actual PhD research?
Yeah, it
Side of
did
things
start
in
out
mind.
with research in mind, and you can really, because it's all been in Git, you can look way back and see how it started. It's really clunky,
Right.
GUI, and stuff like that. And it really started because in our lab, we had one really good scope and one pretty good, like 1 gigasample per second scope, which wasn't quite enough for what I needed to do. And at the time,
mine. I can vision.
right? And like the other one people were using for ultra wideband, it was like a 12 gigahertz analog bandwidth. Like
Yeah.
Right.
50 gigasamples,
Yeah,
I think.
nice.
So anyway, so yeah, that, and I couldn't use that one. They were using it for more important stuff. So yeah, it really just spun out of that. It's like, I need this hardware to do it. So the first version of it was just an FPGA dev board with an ADC I designed built onto it, and then it slowly morphed into newer and newer revisions.
I kind of have a checklist of things that like in projects that I like, and scratch your own itch is always number one. Like that, just because it just means that you're not like guessing at what people want. It's like, no, I am customer number one. I know exactly what I need here. So
Yeah.
that's good. That's a good sign.
Yeah.
And as you said before, a scope can do the job, but it's clunky, right? So if you're doing research on this, you would want to build a more optimized tool for getting the results you want, right? Otherwise, you don't want to have to, for the next 2 years, 3 years of my research, I'm going to clunk around with a scope and manually capture and export the data and blah, blah, blah.
Yeah.
You know, that'd be painful.
Yeah. Yeah. And that's where, people script it all, but it's not portable. There's all these issues like that.
Yeah,
so.
it's just, you have to have the right tool for the job. There's a lot to be said for designing a tool that does exactly what you need.
So at this point, can you explain the physics of it all? So sorry, I didn't have to go over the entries as close as Dave did for the.
He's
Haggerty
already
front.
explained it.
Did I miss it? I mean, so I know that you
Power,
said
like transistors,
Yeah,
like
and
these
some hand
chips, they
waving.
have like totem pole outputs. You know how chips are designed.
yeah, no, I get that.
And
yeah,
they-
I
and
know.
when they
Push-pull
switch,
stuff,
they,
right?
you know,
I get it, but like,
and you can-
but I
yeah,
don't.
yeah.
But the thing I don't get about it is, okay, so you have. I mean, why doesn't it just look? Does each individual pin output have a super discrete different signature from the next one? So can you characterize like every pin being on or off, or do you just look at every pin?
So, I mean, how it works fundamentally is the answer to that question is that you can almost do that. But what I really do as the base is that I'm looking at the data bus inside the chip. So, if you move data from the registers, to read it from the registers, put it on the main data bus, it's physically setting, 3 of these data lines to a high state. Setting those data lines high is basically charging a very small capacitor, which physically takes power. And so on every clock edge, you could look and say, okay, 3 of these data lines were high because there was a large, a spike this large. On the next clock edge, 7 of the data lines are high. And in between the clock, it's going to an intermediate state that they call it the pre-charge state. That's basically halfway.
Right.
Yeah, but the thing that I don't understand is doesn't it matter the order in which those? So you know that 3 lines are high. I mean, it matters which 3, correct?
Yeah, right. That's the important question.
So how does that work then?
This is the question I had. Is that did you have to do this using signature based stuff? Do you have to test the chip that you want to decode and then get a signature map of all the different stuff that happens in there, and then you just once you've got that signature map, then you compare current spikes? Is that how it works?
So I don't actually have to do that. You can do that. That's sort of one of the more advanced
Right.
attacks, because that can tell you, in a single power measurement, it can tell you the exact state of the data bus. What I do is
Right.
I average a few of them, and you basically use this guess and check system where you say, like, if I had, if the secret key byte was some number, 0 times 0, 1, and I know how the algorithm works, and I can say, okay, well, if the secret key byte was 0 times 0, 1, based on the input data I sent to it, the intermediate value, at this point in the algorithm would be something. So if I was just XORing the input with this secret byte, I could say, well, in this case, the secret byte should be, 0 times AB. The next case where I send it a different input, so I say it, send it this input, encrypt. The intermediate state would be something else. So I'll sort of try every possible secret key, and then one of these sets of
Right.
intermediate values should match the power I measured. So,
Okay, so that's like brute forcing a
Got it.
password as well, where you have the hashed value and then you're just comparing it against a lookup table, or you're going and trying every combination as well. Is that is that
exactly.
similar?
So, and what makes it
Okay.
good, because, you say, well, guessing, that's no better, is that for something like AES 128, 128 bits, but the algorithm works on 8 bits at a time. So you only have to guess the 8 bits 16 times. So now you have this 16 times
Right.
256 instead of 2 to the power 128. So one of these is a lot easier than the other.
So if computer architecture, if the architecture of that changed in the future, where it did somehow simultaneously look at or process all the bits at once, would that make things incredibly difficult for you, or would that just change the game?
No, it's they're a little noisier typically, but I mean, you can. So there's an implementation that's doing all 128 bits at once. The thing is, the way the algorithm's designed, it's operating on 8 bits at a time. So it takes 8 bits of the input, takes 8 bits of the key, XORs them together, and puts it through a lookup table. And because of how the algorithm's designed, it's fundamentally breakable. Whether or not it does all 16 of those at once, it can do that, in parallel. That's fine, and it doesn't affect this attack at all.
So okay, so it's just how AES is set up. You're saying
exactly. So, and I mean, they do that because if you try to operate on 128 bits at once, you would need a 128-bit lookup table.
Yeah,
right. So they split it down to make this really small lookup table, the S box. Yeah, so that's sort of the fundamental problem.
So resource constraint is ultimately what allows you to break the code. Because if you had a 128-bit lookup table, you'd be able to do that, right?
Yeah, right. So then this wouldn't work as well.
Now, the first thing that pops into my head when I hear about this sort of attack on a chip is going, well, what effect does the bypass caps have on the chips? Do you have to remove the bypass caps to be able to,
break it?
actually do this, or what?
Yeah, so that's one of the things. I mean, if you're doing it with a physical shunt, then yeah, you would need that. But the trick is that if you can also use an EM probe, like the ones you have, Dave, for doing the
right, of course,
H-field probing, and it's the same thing, right? The current consumption generates a spike.
Yeah, of course.
So yeah, doesn't really matter.
Sorry, so the shunt has to go after the bypass cap? Is that what you're saying?
Yeah, if you're using a resistive shunt, it would have to go after. So you've got to remove them. But you can just use an E-field probe instead.
I thought, there was no way. Yeah, I was pretty sure there was no way it would work if you put it before the bypass caps.
Just be a line.
Right. Got it. Yeah, exactly. You would get
RC response.
Very low pass attenuate. You'd get a very low pass filtered version of the current spikes.
Exactly.
So it wouldn't work. Okay, interesting. So which is better, the current shunt or the H-field probe?
The H-field probe tends to give better results, I think. And in real systems, it's easier because people have done demos where, they take a cell phone and turn it over and just put the H-field probe on the back. Like, they don't take it apart at all, and they're able to do the attack.
Right.
The problem is that you need to position it very, very carefully. So the shunt's easier because, you solder it down and you're done.
Yeah.
So I use that because I'm all about repeatability. If it's research stuff, right, you want...
Oh, yeah, of course. Yeah, you don't want to be dicking around with it. Works one day and doesn't work the next because your tongue's not at the right angle.
15 microns this way and stuff like that.
Yeah.
Right, it's like, no, we're not doing that.
Okay, so I need some more clarification. I'm gonna keep playing the dumb guy. This is my role here. So
it's always your role on the air,
I know,
Chris.
That needn't be said. But anyways, just wait till our guest in 2 weeks. It'll be a bloodbath.
Okay.
So people are using AES 256 type stuff so would that be for like the bit stream, like for programming the chip, and then you're kind of executing a man in the middle type attack, or what then are you ultimately attacking?
Yeah, so it depends what your objective is, but the example I use a lot and using some of the demos is if you have an AES 256 bootloader, someone's encrypted their upgrade file or binary file with some AES 256 key, and that key is on the micro. So the idea being that you can send this binary to anyone and they can only program it into a microcontroller that you've pre-programmed, the manufacturer's pre-programmed with their key.
Yep.
And so you can send it to China or wherever else you want, and you don't have to worry that they're going to steal it.
But isn't that easier? Isn't it easier to just decap the chip and steal the firmware and you're done?
Yeah, you could do that too, right? But this is another way of doing it. So because the key is in the chip, you're able to instead do a side channel attack. So if you just give me a chip, it doesn't have the firmware in it or anything, then I can do a side channel attack on that chip to figure out what the secret key that's programmed into it. And people show this with, FPGAs for I think most of the vendors, like the
Yeah,
bitstream
they all have
encryption on them.
encrypted bitstream. Yep.
Yeah, so people showing attacks against that, if you have a chip, you can get the encryption keys out of it. And the problem is that most of these people are using the same encryption key across a whole bunch of devices, right? So, because otherwise, how do you've got to manage, okay, well, I give this one user this firmware encrypted with chip, whatever key. So
right, you don't want to like laser etch the key for each individual chip, like a unique ID or something crazy like that.
Yeah, so
well, that because then everybody would need different firmware. So that's one example. So it's for people to basically reverse engineer and steal a bit stream, which actually we talked to Mark and Joe from Salier about, right? Because they had that issue, and then it got cracked real quick.
That's right. Yeah.
So what else do people use this for then? Like, what are some of the devious things people could use this for? Obviously, you're testing, right? You're super white hat, right? I'm sure.
Yeah. Yeah. To be honest, I don't know where all of the possible uses are. I'm really on the training and teaching side of it, but there's a whole lot of stuff. Like you look at Internet of Things, and a lot of these protocols, like 802.15.4, Zigbee, Bluetooth Low Energy, they use AES, typically AES 128, to protect their networks. And with any of these nodes, you can send them a message and they'll decrypt it. So any device that you can send a message to and it'll, decrypt or encrypt it is basically vulnerable to these type of attacks.
Okay, so you could send so if you're normally sending garbage to like a node because it only accepts stuff that decrypts as something that makes sense to it, like a packet header that would start talking to it. You're saying that if you went and side attacked it and figured out the key, then you could start sending it legit commands, and that might be the only thing that they were really protecting with. They don't have any kind of handshake or anything.
Yeah, exactly. Like they may be doing something like that.
And then you could go just start looking at someone's drop cam footage or something creepy like that.
Whatever you want to do.
Drop cams are super freaky, by the way. I was where was I? I forget where I was, somewhere in California, but I was I kind of looked up and I'm like, oh, that's a drop cam. That's creepy. It's just I don't know. I don't know why that more than a security footage. I think because it's just streamed to the internet, but something about it just, I don't know,
Right.
Not a big fan.
So where is all the heavy lifting on your side of things done? Is it done in the FPGA or is it done in your software?
No,
on
so
the
it's
PC?
entirely on the software. The FPGA is just shuffling data, so it does the analog
okay, right. So it's
capturing.
just shuffling data from the 14-bit analog to digital converter, which is measuring the power
Yeah,
rail.
exactly. So, it
And
has a
that's
little
it.
RAM in there
Right.
and stuff too, but that's all it's doing. It's none of the analysis is
Right.
on the...
Got it.
I mean, that was a big thing. The software you can actually use with a regular scope. So you don't need the chip whisperer hardware I've
Okay,
designed.
right.
It's,
Ah,
a lot
got
of
it.
people are using that.
Nice. So,
So,
excellent.
yeah, I tell people it's a real...
And that's all open source
yeah,
as
exactly.
well, is it?
So I tell people, it's a real open source
wow.
project. I'm not saying it's open, but,
Right.
non-commercial and
The-
blah, blah, blah.
Right.
It's you can do whatever you want with it. I don't care. It's,
I got a PhD to finish here, folks.
yeah.
I would have kept the software to myself, I think. This is pretty advanced stuff.
Yeah, but so many people have done that it's one person needed to release an
Right.
open source one to really show people how it can be done, right? And
Got it. Well, it's awesome. My white hat
thank
is
you.
off to you. Oh, goodness. So can your chip whisperer attack or your software, basically, can it do other types of attacks, not just the power rail?
yeah,
Or is-
all it's doing is power rail. So the differential power
right,
analysis
okay.
attacks. So
Got it.
some of the demos do other stuff.
Yeah, but I thought it could. I can't remember the precise details, but you're talking about you can actually spike the power rails as well.
Oh, yeah.
Is that right?
Yeah, so that's
and you can change and you can intercept clocks and things like that, and you can change the jitter on them or something.
Yeah,
or is
no, that's right. So that's on the capture side. So not really the analysis. That's the hardware again. It can do that. So it
right.
can you can do stuff like if you drop the power, at very specific instance, you can skip over a check
Right.
and stuff like that. So if it says is the password okay? And right at that moment, it just says oh, yep, it's okay.
Okay, so your hardware can actually dip the power.
Yeah, all it has is like a MOSFET basically. So it's doing a, crowbar type thing. Just very short, like, nanoseconds possibly.
Right. Yep. But it sucks all the energy from the bypass cap, and then boom, it's got to charge back up, and that gives you a droop in your
exactly.
rail.
So.
And what can you do? What's the advantage of what can you do with that sort of attack as opposed to the power rail?
I mean, that sort of attack, the power rail is very specific. It's breaking encryption. That's more or less all it's doing. Whereas the glitching type stuff, you can do stuff like if there's just a check at boot, it checks, is this signature valid? And people have used this for a while. Yeah. They loaded firmware that doesn't have a valid signature and they just glitch past that check. So the glitching's probably even more powerful, but it's less precise. There's no real math behind it here. It's just you screw around a bunch, and at some point, it works at the right time.
I've heard that there was a many years ago, before Chris was born, there was an attack on one of the early PIC micros, and it involved pulsing the programming line voltage high, or it was the power rail or something. You would actually pulse it high, and it would allow you to bypass the encryption on the firmware. It'd allow you to bypass the bit the security bit. That's it. So it allowed you to bypass the security bit and actually read out the firmware. So you'd pulse the chip, and then you'd be able to read the firmware just straight back out, even though the security bit was set. And it at least happened on the PICs.
Yeah, there's a guy, Sergey, I forget his last name, but he had a PhD thesis, I believe, on the topic of bypassing protection on microcontrollers. And he was using a lot of that. So he did some of the AVRs, the earlier AVRs as well.
Maybe that's where it came
PICs,
from.
I know, and possibly some other ones. But
yep. Yeah, I think there were some others as well, and it was quite a common technique. And I think at the time it was all the rage, and everyone was going out trying to pulse these micros, seeing if they could actually bypass the security bit on them. And yep, I think a lot of people had some success. And I think there was one manufacturer who even came out and actually said, "Oh, our chip is, pulse protected or something. It can't, this sort of attack can't happen on our chips." It was like a selling feature or something.
Huh.
So
seems like they're just painting a target, right?
Yeah, come and get us.
Yeah,
can't break us. Oh, really?
Yeah.
Really? We'll just measure your power rail. You're Gonski, dude.
So Colin, what is there any way to actually? I don't know if you're maybe not allowed to give away these secrets, but is there any way to?
Of course he is. It's all open.
Oh, that's true. Good point. Is there any way to actually protect stuff? I mean, so we have listeners who are developing embedded projects. Is there a legit way to actually protect it against, this kind of attack or other attacks?
Yeah, that's always the question. So to be honest, I don't do that side as much. I'm more on the attack. But that's the easy way. But, no,
just tell us all the ways it can happen, and then we'll avoid
I score
using
goals.
those.
I'm not a goalkeeper, right?
Right.
But yeah, there is. I mean, as I mentioned, using the physical devices designed against this is one of the better ways. So most of the main manufacturers make secure devices that are designed not to do this. The downside is most of the time you need to sign NDAs and stuff like that. You can't just
to
buy
get
them at DigiKey.
Yeah.
So if you're stuck in the software side, there is a good book on attacks on smart cards, and it talks about a few of the countermeasures. Most of these countermeasures end up being breakable or broken at some point. So, it's not a sure thing. And a lot of it just becomes, what's your threat level that you really care about that is worth doing? Yeah. And to some degree, the answer is always going to be, you should think about, what if someone can break it? Yeah, so you should be using separate keys everywhere, stuff like that, and figure out a way to make it work. That's the better answer.
Or just go, couldn't be damned, I'm just going to make everything open source.
Yeah, right. So.
And then,
Or just write everything in like Fortran, and it's like, no, I'm not going to bother.
Not even worth it.
Yeah.
Still comes down to assembly language.
Yeah,
dude.
no, that's true. Yeah.
Still I mean, not assembly. It still comes
Machine
down
code,
to
yeah.
machine code.
Yeah.
Yep.
Yeah, no, I mean,
But these secure chips are the way to go, though, because they not only stop, power rail attacks and software attacks, but they stop physical attacks too. Like they've actually got, metal overlaid, like barriers, physical barriers inside the chip that overlay the flash area and stuff like that. So even if you decap the chip, you can't sort of like laser probe it and all that sort of jazz, So yeah, it's not just the software or power pin side of things.
I still have some trouble. I mean, if I'm being honest, this is part of the trouble I had at DEF CON 2. I kind of just don't get it sometimes. Like, maybe this is the analog in me coming out. I'm like, so why would people do this stuff? I mean, so I guess the commercial aspect is, stealing stuff, but you also get that example of, I think the IoT example is actually really good for intercepting packets that you thought were secure. Are there any others that...
Yeah, a lot of this started with stealing satellite TV, right? That was like the number one thing for the longest time.
Yeah.
And like they were attacking chips with fibs, like focused ion beams, the, electron microscope type stuff. Like,
all for HBO, huh?
Yeah,
and this is before Game of Thrones.
Basically, all it comes down to is people just need to be able to steal something. That's it. Either they steal money or they steal content. Take your pick. But either one is going to be justification for doing this sort of stuff.
Yeah, absolutely, right? Like, it's crazy they're stealing... I don't know how much it was back then.
So they're either stealing content on their HBO channel on their satellite thing, right? Which is all the rage back in the day before it was done over the internet, and or they were stealing, like a SIM card, data, so that they could steal somebody's card and use it to buy, go to the shop and buy something.
Yeah, true. That's a big one now, right? Too, and I mean, smart meters with those coming out, stealing electricity, that'll be another.
Oh, right, stealing electricity.
Thing,
people sort of, hack their smart meter. Yes.
I feel like so much of this stuff, though, so much of this stuff could just be handled by, actually not by the hardware side of things, as much as that's heresy. It's just like, you could do it with SPC, like statistical process control, where it's like, oh, well, Dave Jones was paying $80 a month for electricity, and last month was $10.
Right. Yeah.
Maybe something's happening.
Yeah.
They do monitor that sort of stuff. That's how they find drug deals.
Yeah, I mean,
actually,
yeah.
Right? If a house suddenly goes from, X amount of power per year, it suddenly goes to like a megawatt, like 10 megawatt hours, they know they're running all these heaters up in their roof to actually grow all their drugs, and stuff like that. So they actually rate them. And there's actually that's actually done. So believe it or not, there's a lesson.
I guess there's always going to be low level stuff that needs to be protected, though. But I guess I just have. I mean, I've always had trouble with this because I don't understand. I never thought about the attack side of things. So that's why it's been tough for me.
Yeah, I mean, the other thing is like the PlayStation and Xbox, right? People breaking those for. Breaking the bootloaders to use.
Once again, it's content again.
So.
Exactly. They don't want to run their own stuff. They want to copy the games.
Yeah.
That's what they say in court when they dragged him to court. Why are you doing this? Oh, because I want to be able to run my own stuff on there. No, it's because you want to get the pirated games, dude. It's got to be a financial incentive somewhere.
Yeah, exactly.
Like some people just do it because they can, right? But yeah, there's going to be orders of magnitude more people if there's a financial incentive to do it. So, yes.
Well, yeah, that's like the Internet of Things stuff, right? Too. You can, if you put a light network up somewhere that's unsecured, some bored college kid is going to try to hack it, right? Just play Tetris on the side of your building. So
yeah,
exactly. All these threats, right? That people don't think of. It's
right. Never underestimate the tenacity of a nerd.
Oh yeah, exactly.
So what? You're halfway to your goal at the moment. Why was your goal 50,000?
So it was based on there's a local fab I'm trying to order 1,000 units through. So sort of based on some of the money we have, from selling stuff already, how much extra money we need more or less to order 1,000 was sort of what it was loosely based on. So that was about.
Got it. And they're all going to be made locally in
here in Nova Scotia. So there's
Canada.
a fab sun cell we work
Nova
with.
Scotia. Awesome.
I actually experimented quite a bit with getting stuff made in China and stuff here and whatnot. And in the end, it's nice to support someone local. Everyone likes that. Support local. But yeah, it's cheaper by the time you work everything through, and there's no quality issues that I had.
Yeah, exactly. So. And if even if it's not necessarily cheaper, it's just less hassle.
Well, yeah, that's what
right?
I factor in a lot of hassle money there, and
yeah. So if you can build that in, and because you've got a niche product, you can build that into your price. It's not like you're doing a Kickstarter for a new shield for the Arduino. It's going to cost $10, right? Where you'd have no choice but to make it in China because people expect a low cost. So for these niche sort of things, you can build that local factor into your price.
Yeah,
of your product.
And the other part of it too is it's a pretty complicated design in terms of there's a lot of analog portions to it and whatnot. So when you're going to China, they'll often just substitute, whatever part is close enough to what you specified.
Yeah.
Like you specify these nice whatever capacitors. Like, this is close enough. So having it local, it makes sure it's all legit
what's
parts.
10 what's 10 picofarads amongst friends,
yeah,
right?
Yeah, so.
Right. That's why I so didn't send my microcurrent to China, because it's got like a $4 resistor on there, and I don't want them going out to they'll totally go out and source a 4-cent resistor. I'm going but that's the whole key to the performance of the product.
Yeah, well, I did that with I had some ADC boards made a bunch in China, and I sent them SMA connectors because they would always just find some gold-plated
crap ones
like that. So
this
cast
one was made out of granite. It was super low cost.
yeah.
So you said you sent some over there, and so like small runs, big runs. What was that experience like? I mean, what ended up happening with some of those? Did you have a bad experience?
No, I had an okay experience. So like I did. I've done a few really small runs, like 5 or 10 units in China, which I actually found them cheaper than anyone local, because China's NRE fee was like $100 or something like that, right?
Yeah, right.
They could just have people placing the parts, whereas here, that's not cost effective at all. They need to program the machines, right?
Not my assembly
really?
here.
Okay.
I can just give them one. I can just give them one board or 10 boards, and they'll just.
Okay, are they reasonable, or are they?
Yep.
What's it? Okay.
Yeah, they're pretty reasonable cost. Yeah. Yep. So, and of course, if they just hand place them, then there's no, there's no machine setup fee or anything like that. So, yeah.
Yeah. So that's what was killing me is.
So for those sort of short runs, it works well.
Yeah. So that was sort of my experience, and then they did substitute tons of parts. That was always the thing, right? It's like everything.
Yeah.
Even connectors was the annoying thing. You want nice-ish gold-plated connectors, but not a chance. So,
what's that? 30 mils of gold? How about gold flash?
Yeah. Oh, not even, right? It's tin. So,
right.
And just crappy.
Right.
They just doesn't feel as nice. So it's like, yeah. So it's good for prototype, and I don't know. If you send them critical parts or stuff like that, that's been pretty successful, actually, for smaller runs, but...
We had that at Altium, right? We were having our stuff made in Shanghai, and one of the assemblers substituted a header connector. One of these surface mount. Surface mount header connectors, right? So we got these boards back, and all these connectors were all melted, and all the pins were all at weird angles because the plastic they used in these headers was so crap.
That was actually chocolate. Yeah.
Yeah. And I've got a photo of this, just totally distorted connector after it went through the reflow process, and it's just, thank you very much for that substitute. Unbelievable. Yep. So some of the parts aren't just fake, they're like just totally crap. They won't even survive a simple reflow. Basic stuff like that. Crazy.
Oh, yeah.
Hand solder, they will survive just fine, because you're only heating up a single pin at a time. The whole thing doesn't have time to come up to temperature and all that sort of jazz. So survives just fine, but whack them through a reflow and it's gonski. Let that be a lesson to you, folks.
Yeah, well, I had one board too come back with all of the, I think it was like the 10 nanofarad decoupling capacitors were inductors.
Oh,
So
nice.
that was tricky to
Nice.
power it up, right? And, oh no, why is it all
Right,
shorted?
yeah.
So yeah, I just swapped them all in.
There's some capacitance there.
Yeah.
I've had that happen. You go, yes, I found the short. You power it up again. No, there's another one. And you just keep going.
Well, when at first, when you measure it out, then there's that moment where you go like, oh crap, did I short the PCB rails or something like that, right? Is this
Right.
is this fixable?
And how did you find the one in Canada? I mean, it was just a local referral type thing?
Yeah, there's only one here, basically. You got one choice. I mean, there's one another like 2 hours away, but around me, that was it. So, I mean, there's a lot more across Canada, but it's nice having someone local, and they have pretty good low volume prices and stuff like that. So, I was happy.
I'm having a look at your board again. You've got a nice looking low noise amplifier on there. What sort of levels are we talking about on these power rail things that you have to analyze? Because you've got a 10-bit analog to digital converter at 105 meg samples per second, so that's a bit of a beast. But you've also got a low noise amplifier coupled on the front end.
So you're really measuring, like, if you put I'll often use about a 50 ohm resistor across, if it's just a small micro, and you're just measuring the drop across that resistor. So it's pretty small fluctuations, like, the constant DC power you don't care about, just the changes. So something like, 10 millivolts is pretty regular type levels.
10 millivolts at what speed, you said?
Right.
So like couple megahertz?
Yeah, I mean, the speed you measure at is a function more or less of the clock frequency of the device, because fundamentally every point you care about is the clock edge, right? Like, that's when the lines are switching.
Right.
Got it. Yeah.
Obviously, there's some issues. You got to get the right time,
resolution right there.
Yeah.
So how much do you have to oversample? Say with your 105 meg sample per second one, what speeds can you actually?
Yeah. So the whole chip whisper thing, what makes it better than a regular scope for this work is that you can input the clock and it uses that as the sample clock.
Oh, got it.
Yeah,
so
it's all synchronous, and it doesn't, like, you can put a clock into a scope, but it's got to be 10 megahertz and stuff like that, right? Normally, so this you can put anything in, and it'll multiply it by. I often use multiply by 4, and almost the only reason you don't need to do that, you can just use one sample. But when you look at the waveform, when it's multiplied by 1, it doesn't look very exciting. It's just like a line, that
right?
Because it's 1 point on each thing.
Right, so you can go up to maybe 25 meg with a decent amount of
like 25 megs, no problem.
Room in there.
You can, I mean, you can do ×1. So if I've attacked.
Right, so you could go up to 100
and you can
meg.
even do some undersampling stuff, like the actual frequency, the bandwidth that you need is pretty small, typically like 20 or 30 megahertz of bandwidth. So like some people will actually use just a down converter, like standard SDR type down converter, to measure, gigahertz devices running encryption, and they just down convert it and sample, 10 megahertz of bandwidth or whatever they need.
Right. Does the synchronous sampling have any other advantages over using a scope?
No, it's primarily that you don't need as high a sample rate because you get on every clock edge.
Right,
so
got it.
The issue that people run into is they use these really fast sample rates, and really the only thing you need is the moment, the device starts the encryption to the start of the sample clock. This is sort of this random jitter. Like if you have an asynchronous scope, it could be whatever.
Does the amplitude matter, or are you effectively getting the digital output, really? If you know
like
what
the
I mean.
amplitude of the power signal, you mean? Or?
Of the pulse. The amplitude of the power glitch. Does that matter? Are you from the amplitude? Are you able to differentiate between one? Oh, it just moved data to the X register, or moved it to the Y
so you
register
do need the
because
amplitude.
this
That's why
is
it
higher
has like
amplitude.
the 10-bit. So
Right.
higher bits
Okay.
is
You
better,
do need it. Okay. Right. So that will keep our esteemed colleague Chris happy here because it's analog domain, dude. There you go. It's all analog.
Yeah.
It's not just. It's not just digital.
Oh yeah, lots
Right.
of analog.
Hacking. It matters.
Well, yeah, lots of analog, but you still got to
What-
script this thing in Python. So,
Yeah.
Ugh.
Yeah, FPGAs, Python.
That's software. Right?
Oh, I love that. No, I love FPGAs, but I don't know, something about Python still.
It's too easy.
Right.
Is that's probably it, right?
Yeah.
Feels like there should be
Just-
more.
Except
Yeah.
we have no clue how to do it, so
Yeah.
we're just Luddites, you know.
Yeah, you should try. It feels dirty when you use Python.
Oh yeah.
Well, it's just like, there's no, like, it's not an int, you just assign variables.
Yeah.
It's like, if you
Yeah,
think
you're like,
something
Right, yeah,
should
yeah.
happen,
Semicolons.
structure.
Screw
Yeah.
you, semicolons.
well, no, you can put semicolons in, and it doesn't care. That's the best part. Because I always put them in, because I'm writing C,
Awesome.
and then switch,
Right.
right? Until I'll look back, and like,
Right,
it doesn't
yeah,
even
yeah.
give you a warning or anything.
Really?
It's just cool. It says, you know what?
Breeze.
I know what you need. Yeah.
It's like the dude of programming.
yeah.
It's like just yeah, man. Yeah, whatever.
Chill
Yeah,
out,
no big
man.
deal.
Chill out.
Just make sure you get your white space right. You know?
Yeah. It's OCD.
So what happens with
Yeah.
what happens with chips with built-in clock phase lock loops that actually, like it uses an external crystal and then it's bumping up to 400 megahertz inside the chip?
Yeah, so if you want to do the synchronous, there's a few options. One is you can just use a PLL yourself externally. So the full chip
Right.
whisperer hardware does have a PLL, and inside the FPGA there's some configuration that's built in to let you do that. So if you need to multiply the clock by some arbitrary amount, you can do that. Or the other option is you can do basically clock recovery. So if you're using a totally internal oscillator, that a lot of smart cards will do this. They have their own internal oscillator to help desynchronize stuff. But you can just, in communications, clock recovery they use all the time. So you can build a circuit that just pulls the clock out, typically the strongest harmonic, and then uses that to do the sampling.
Can I ask a dumb question again? Sorry. Can I ask a dumb question? What is a smart card? What is a smart card?
So like, credit card with a chip and pin. Do you have
Dude,
chip and
you
pin
don't know
now?
what a
Did they
smart
bring
card
that
is.
out yet?
Chip and pin is not big in the States. I just got.
Oh, this is America.
I just know-
That's a back way. People are still buying their groceries with checks.
Yeah, no, seriously,
America.
the discount grocer by me
Right.
does that, and it's always a long way. No, I literally just got my first chip and pin card today.
Wow.
Yeah, it's stupid, right? So thank you. That's the one I didn't understand that.
That's smart.
Yeah. Okay.
Right.
Yeah, so that's a smart card.
Now, what was I going to ask?
Yeah.
Something just occurred to me. How you could possibly avoid having your product attacked in this way. What if you had a spread spectrum clock, random spread spectrum clock powering your product?
Yeah, so I mean,
Would that screw up your thing completely?
so if you do the clock recovery on that, it's still. So there's one example I have where I program an AVR to it uses the internal oscillator and then switches it between 4 to 12 megahertz. It's
Right.
spreading it, over this huge range, way beyond what you legitly should do. And it's fine because you can do the clock recovery on it, and you can do that in software. And
I was going to say, you could. You're part of your firmware. You could always constantly and randomly switch the internal clock to different frequencies. Boom, 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 boom.
yeah, it complicates things, but it's not. So
Right.
actually, that's not a bad
It's
idea, though,
not
right? If
the
you want a
deal.
simple thing to do, but
There you go. There you go,
There you go,
folks.
yeah.
Simple technique is to randomly adjust your internal clock. If the exact clock rate doesn't
Of
matter,
course,
like you haven't got a UART
troubleshooting
or
your other
something.
problems would be a hell of a time, right? My spy line is just a mess, but I'm super secure.
Right.
no, I mean, I think some smart cards do that too. And they'll have multiple clocks they'll switch between so that you don't necessarily know which one the crypto hardware is running off. So they have all the
Got
clocks
it.
running at the same time, or different phases on them.
Ah, nice.
So-
Yeah.
Right.
But
Jumping between phases
yeah,
there,
dealing
nasty.
with timing on that, that gets crazy. The digital side.
I think someone
but-
who's already at the point where they're like, all right, I'm going to sit down and I'm going to be side channel attacking this card. They're not going to be like, oh, they switched one frequency. Guess I'll go get a sandwich.
Yep.
I guess I'll pay for my
I'm done.
TV.
Yeah, right.
Yeah.
It's not like there's going to be giving up. It's just a matter of time kind of thing,
Yeah.
So I wanted to go over the hardware as well. So we know there's an FPGA on board. Is there a place where I can see the hardware, or a good place to?
Like just the board,
Look
you
at
mean,
this.
or a schematic?
Yeah,
Or just
There's
on
lots
the
of great
schematic.
photos
Yeah.
on the Kickstarter. There's lots of
Oh.
great photos on the Kickstarter.
Sorry, I was on the Hackaday.io page. I'll go to the
right.
Kickstarter.
No, that's the old.
Yeah. I think I put one photo of the new one, but I haven't updated it fully. Actually, yeah, there's a whole breakout of everything that's on it on the Kickstarter.
Yeah. Okay. And so, also, can you explain the difference between the old and the new one? So, what has changed between the light and the normal?
Yeah, so the normal one, some of the background of the normal one, I wanted people to be able to build it themselves. And to do that, I used an FPGA module, that had the BGA FPGA
Right.
on it, so
Yep.
that they didn't have to do that soldering. So one of the objectives of this one was to make it cheaper, which meant making it on one board, and to keep it hand assemblable, switching to a TQFP FPGA. The only TQFP
Yeah.
FPGA is small. So the LX9
Yes,
instead of
I know.
LX25.
One of
Oh,
our pet
yep,
gripes
yep.
here on the end.
Yeah, so anyway, I switched to that.
yep.
To do that, it drops a few features that a lot of people don't use. Primarily, the old system can trigger on an analog pattern. So it can say, here's a pattern of, when the encryption happens, look for that pattern real time in the data and then trigger the capture. So this one can't do that. It's
Right.
missing. It's missing. There's some other stuff, like the old one had an external PLL. It had level translators. Those are removed to save cost. And the old one had a whole bunch of jumpers for the target device because it was designed to work with all sorts of stuff. This one just has one target device on it. You can still interface other stuff to it. There's a whole half that breaks away, but basically it's taking it and making it, one board, no jumpers. There's no through hole on it, so that saves a lot on the
That's
assembly
smart.
cost.
Yep.
Yeah, so it's really just making it, one board for training, and then you can use it afterwards. But whereas the old one sort of developed.
Do you have full tutorials and stuff like that? That it comes out of the box. Does it run a tutorial to to teach people how to do this sort of attack?
Yeah, that's the objective. So right now, there's all the tutorials from the old one, and almost all of them work, almost as is. There's different jumper settings and stuff like that
Right.
that I need to document, but that's sort of the objective. I warn people in the Kickstarter, it's not like, oh, if you've never used a compiler ever before, it might be a little tricky for you. Not
Right.
impossible, but to get the most out of
Risk
it.
and challenge.
Yeah.
There will be
Right.
code.
Yeah,
At some
exactly.
point.
Right. So, I mean, if you're doing this stuff, you should know what code is and how to do it. Otherwise, what's the point?
Right.
I don't know. To seem cool.
I've just started with my Arduino, and I want to get into hacking 256-bit AES encryption.
Yeah.
I just got my first multimeter. Will that help?
Yeah.
Right.
So no, so that's sort of what it's aimed for.
Yep. Sweet. Well, I hope you get there on your target. You're almost. Come on, people, get one. This is
Right.
a
So,
very cool product.
So Colin, who do you imagine would buy this that might not already be buying this kind of thing? Is it like fledgling security people who are already making embedded devices that should be worried about this kind of thing? Who are you targeting with all this stuff?
So it's a huge market, to be honest, because with the main Chip Whisperer unit, we've had, everyone from hobbyists have bought it that just want to get into this more. And that's still an interesting area. So, people going to DEF CON that are just interested in, hey, how does this work?
Right.
Obviously the embedded side is what I really want to target. The whole point of the whole project is really to show people, hey, if you're doing security on embedded things, you should, consider this as a real threat when you design your systems. So,
So you imagine that, okay, so someone is making a new device that they want to sell, and then they should buy a chip whisperer and then actually try a side channel attack to make sure that they can't break it without tons and tons of hassle, kind of thing?
Yeah, exactly. Something like that. Or even just to learn. I mean, a lot of it's just learning how the attacks work. And then when you design a product, you'll have a rough idea, how secure it is. Right. You really don't have to do the testing for a lot of stuff you do. You just know, like, oh, this will be totally breakable. But you might not care, right? It might be like, well.
Of course.
Yeah, you should go like hack a Nest or something like that, just so that people sit up and pay attention. Yeah. It's like, oh, hey, maybe my thermostat should be dumb.
Lot of that'd go straight onto all these social media sites. It'd go viral if you had a video that let's hack the Nest. I can turn somebody's house into a furnace.
Yeah.
That would
right.
It's got to be done.
Send her the thing from the street to turn on the air conditioning in the winter.
That'll show you.
Yeah, seriously. You and your
let's bring this
fancy design
$500 million company to their knees. Awesome. Sounds good.
So there's an FPGA on board, and then what was the other one? The SAM3, is that right?
Yeah, so I'm using SAM3, Atmel SAM3 for the high-speed USB, and
is that an older chipset? That sounds familiar.
It's old enough that I was going to order a dev board, and then I was looking through my stockpile, and I had one, and I didn't even know. Because it was from like 4 years ago, some project, right? So,
all right.
But, it's pretty basic high-speed USB chip. There's other people were asking, why don't you use an LPC one, I think? There's a bunch of them that have this, but basically I use the external memory interface and just memory map the FPGA registers right into the...
that's nice.
Yeah, so it's really easy to do data transfers and stuff. I just point the USB at the FPGA and do that. So
okay, but now the critical question: what happens when someone uses a chip whisperer on a chip whisperer because you just have that memory line exposed?
Yeah, well, it's all open, right?
Doofus, because it's already open.
Wasting my time here.
That's funny. Yeah. Well, it's cool. Yeah. I think this is and so you teach classes as well, right? I mean, so you will actually teach people how to use this thing, or how does that work?
Yeah, so I've done training. I did a training last year at Black Hat as a 2-day embedded security training, and I'm running one again for a company in a few weeks. So I've got to make some more material for that. And I plan on running training courses, if there's interest more or less on.
I was going to say that's a good place to make your money.
Yeah, and that's the thing. That's why I can do open hardwares.
You can do security consulting. Companies pay huge dollars for this sort of thing.
Oh, yeah. And the funny thing I learned is that I can put everything online. I can put all the tutorials online. And people will still, big companies will pay for, a 2-day training. I can tell them, I'm going to use this material that's free.
That's available for free.
I'm literally going to be reading off my website.
But I will happily charge you $1,000 an hour to come talk to you.
But no, people have training budgets and stuff like that. And they just...
Totally.
No one has time. If you say, read this, no one's going to do it. Right. If you say, come to a 2-day training, they'll learn.
There's coffee.
Totally. Yeah. That's right.
So that's gone pretty well so far, though. I mean, what is the profile of people that are taking that kind of training?
So really, the one at Black Hat, it was pretty random. A lot of people doing embedded stuff, but there's been there's whole fields I didn't really think of. Vehicle stuff is pretty popular right now, in fact, because people are apparently it's a big threat model, right, of attacking cars or cloning modules and stuff like that. But it really varies. Like, there's no one group.
That's the one thing I got out of. So I mean, DEF CON was weird for me, but the one thing I got out of it was kind of like, you should probably be afraid. It's not because oh, the world's coming to an end, but just because it's not something that people think about. It's not like stuff that like I said, I never think about this stuff because I don't do embedded, but also because why would people even bother with this stuff? But then you start thinking about high-value targets, stuff like that, cars, like you said. I mean, I think about industrial applications especially. There's a lot of vulnerabilities there. And for years, embedded has just kind of gotten away with security by obscurity or by having no interface to it. And then now everybody wants to put the Wi-Fi module or a Bluetooth module on something, and it's just like, well, good luck with that. Yeah. Oh, an IP address on everything? Well, guess what that means? It means that, grumpy dude in his basement now can access it from 10,000 miles away.
Well, that's what I tell people. It's like, if I was buying a house, I would definitely want light switches wired, right? Don't give me any of that Internet of Things, whatever.
None of that Nest rubbish. Yeah. No.
Are they really not wiring houses these days?
Well, that's what they always, when we were doing our Internet of Things low power wireless, they said like, oh, we're just going to run power to every light. And then the control will be wirelessly and you can just stick a light switch anywhere. I don't know if they did it ever, but I've heard that so much.
Yeah.
I just assume someone did somewhere.
It's stupid. You can't beat a switch. It's just always there. In 50 years' time, it's still going to work. People are in houses a long time, It's not...
Yeah.
Unbelievable.
Well, I think, it's okay to have, like, brokered systems where it's, like, both, but you always need a fallback, right? It's just like...
Yeah.
Even if the fallback was, okay, so now you have, like, a system where it is wirelessly controlled, have the default be on. That's fine with me. You can turn it off the circuit breaker. It seems like some of these, like, from a system design perspective, some of that stuff is just like, I don't know. You said you'd done like IPv6 as well. Does that end up changing things for the whole IoT space or security stuff at all, or no?
A little. I mean, with the IPv6 and IP, people are running, some sort of IPsec or something on top of the lower layer protocols often that will add security onto it. But at the end of the day, you still are running some sort of encryption algorithm on these small nodes. So there's still attacks you can do against the public key encryption implementations on the end node. So there's still lots of attacks available on it. It might not be the AES at the lower layer. It might be some other layer.
Where can people, Colin, where can people follow you? Do you have a main website? I know you've got the...
I have a...
You've got like a GitHub thing. You've got you've got the Kickstarter page.
Yeah, I have my own
where's all your
website,
stuff?
ColinO'Flynn.com. Easy to remember. Yeah.
Duh.
But yeah, it's... I don't know. I'm not very good on the whole, Twitter and social posting projects. So I do have a few things there. But yeah, Twitter maybe.
What's your Twitter handle?
Colin O'Flynn.
Colin O'Flynn?
Yeah.
Too easy. And that was available. Somebody hadn't stolen it.
No. Luckily, right? That was the...
Well, until they do a side channel.
Yeah.
That's all you...
for the longest time, like C.O. Flynn was widely available at the beginning, but then a lot of Ireland started to get on the internet, it seemed, and that just killed me.
I love it.
Yeah.
Well, thank you very much for joining us, Cole.
Oh, thanks for having me.
Yeah, definitely. And people should definitely check out the Chip Whisperer Kickstarter. For sure, we'll link that in.
Yeah, absolutely.
And if you're developing an embedded project, you probably want to try this out. You definitely want to get a Chip Whisperer and make sure that your device is secure. So I would definitely recommend going to check that out.
You should just have it in your kit just in case you might need it one day.
That's a good point too.
You should buy two
as a recommendation,
just as a
or 10, whatever.
There's a 10-pack there conveniently.
I saw that. Yeah.
Oh, okay. I thought you weren't allowed to do that on Kickstarter.
They always change the rules, right? Now you can do up to 10.
Do they? Okay.
Because originally it was nothing.
Right.
It was
okay. And then they changed it, and then it's right. It's back to 10.
Yeah.
Okay.
So if you're a classroom or something, universities sometimes want a bunch for a lab, but
got it.
Yeah.
Awesome. Thanks, Cole.
Thanks, Colin.
All right. Thanks, guys.
Talk to you soon.
See ya.
See ya.